Hi students, am I live? Am I audible? Let me know in the chat box. Hello everybody, welcome back to Vedantu JEE English channel. How is everybody doing? How is your potential energy right now? Can you hear me? Hi. Hi Mithyas. Hi Pandu. Hello Vemi Shetty. Hi, welcome back. Oh, I know you. Hi Anugna. Hi Srihita. Good evening, bacha. Good evening everybody. Chalo. You can hear me well, see me well. That is it. That's all I wanted to know from you guys. Uh, 1 second. Yes. Okay. Okay, so this is a very important session, especially if you are taking this JEE April attempt, which is just in a few days right now. We are going to do the organic syllabus. So many questions from the organic syllabus. How have I curated these questions? First thing that you should know what you are expecting out of this session is, first of all, we're going to talk about all of the effects that are there, right? All of the effects that are there, electronic effects, resonance effect, mesomeric effects, all those effects we're going to talk about, right? And then aromaticity, all the things that are there in the general organic chemistry. And then we're going to move on to some important reagents, the reagents which are repeated every year, that you should know that how to solve those reactions. We're going to look at all of them. I'm going to tell you how to approach those questions, how to find the trick and tips to never miss any reaction that ever comes in your exam. Because right now, after seeing the pattern of the exams, bacha, I am telling you, now the reagents that are asking, right, like there will be a reaction and the reagent will be written on top of it, right? That reagent is like from the very basics of chemistry. They are not going into the depth of chemistry. They're not asking you out of the world reagent. They're asking you very basic things. So you should know the basics of chemistry. That's what I'm going to teach you in today's lecture. So get ready everybody. Hi Tanishka. I know Tanishka. I came over Tamil. I know few of you students. Okay, let us begin. Before that, again, as we share some news with you guys, as all of you must be aware right now that Vedantu is offline. If you want to learn with Vedantu in one of its offline centers, then you can check out that there's a link in the description box below. Click on that link, and if Vedantu is available in a city, you can join that. But if you are from Patna, bacha, we are organizing a mega dhamaka event in Patna. You can come join us, ask us your questions, ask us. We can give you career counseling. Everything would be there, what to do, what not to do in your 12th, even if you're in 8th standard. So we are preparing for JEE, NEET, 8 to 10 foundation, whatever. You can come join us at the Patna Center. Right? Hi. Chalo, now we are back to the basics. Very first question on your screen. How we're going to go about it? There will be a question on the screen, right? First of all, I'll be asking you questions and then I'll be explaining you what the right answer is. The first question is on your screen right now. Can everybody see that? The functional group that shows negative resonance effect is. You have 4 options in front of you. What do you think is the right answer to this? These kind of questions are very repetitive. Every year such kind of questions come. Either these questions or even like what are meta-directing groups, what are ortho-para-directing groups, right? So these basic things are asked every year, right? So right now, can you see in this form of this question? First answer I've gotten by Sanjay. C answer, very good. Then Vemi Shetty, Tanishka, keen vibes, very good. I've received similar answer from you guys, correct? So what is negative resonance, bacha? Whenever there's a word called negative resonance, just imagine a benzene ring in your head, right? Just imagine a benzene ring, right? All the other groups present over here, like OH, oxygen has what? Lone pair of electrons, right? So if on the benzene ring or OH is attached, then this lone pair of electron will do what? It will resonate inside the ring. Can you see? It is giving the electrons to the ring, and therefore it is doing what? It is increasing the electron density in the ring. Understand this. What it is doing? Increasing electron density in the ring. ring. What does that mean? It means that it is making your benzene ring more negatively charged. Remember that thing. It is making it more negatively charged. Same is the case with OR. OR, again, oxygen has lone pair of electron. It will donate inside the ring. Similarly, look at NH2. NH2 once again has lone pair of electrons. It will again donate the electrons inside the ring, making the ring what? Electron rich. But what does COOH do? Bacha, remember one more thing. A very nice funda I'm going to tell you. Whenever you see any compound with a multiple bond, just like COOH has what? A multiple bond in it, right? So all multiple bonded compounds will always and always show what kind of resonance? Minus R. Minus R means what? Let us look at the resonating structures of COH. Can you see that as the OH group was giving the electrons to the ring, this is doing what? Instead, it is taking away the electron from the benzene ring. Can you see? Can you see? So therefore, it is said to show minus M effect or minus resonating effect. Is this clear to everybody? Is this thing clear? Very good. Let us go to the next question. Next question is, ionic reactions with organic compounds proceed through. Again, a very, very important kind of questions. What are free radicals? What are carbocations? What are carbanions? Every year, questions based on this will be asked. So I'll tell you a few of the basic things about each of these things. First of all, try to attempt this question. I'm looking at, okay. Yes, pakka clear. Very, very good. First answer I've received by Ratna Kumari B. Hydrolytic bond cleavage. Very, very good. Then Vemi Shetty has also given me the correct answer. Ramakanta. Very good. Okay. Okay. Tanishka. Correct. All your answers are correct, bacha. Ionic reaction. So what is homolytic and hydrolytic cleavage? For example, this is the R group, right? And this is another R dash group. Okay, understand this thing. One bond is made up of two electrons, right? And every covalent bond is made by sharing those two electrons, right? Now, if I want to break this bond, there are two methods to break this bond. Number one method is homolytic cleavage. Homo means when I break this bond right from the center, then what am I getting? I am actually getting two free radicals. Can everybody see that? I'm getting two kinds of free radicals. But if I do a hydrolytic cleavage means what? That one of the atom which is more electronegative will take away both of the electrons, and hence what are we left with? This is called hydrolytic cleavage. Hence, bacha, what happens in this case? We are left with the R positive and R negative entity. This is called the ionic entity. Is this thing clear to everybody? This is the hydrolytic cleavage when one of the atom takes away all of the electrons. Which atom is that? That is your more electronegative atom. Whichever will be the more electronegative atom will get the negative charge, obviously. Correct? Now let's move on to the very next question on your screen. Which of the following compounds will be most easily attacked by an electrophile? What do you think should be the answer of this? Electrophile. Understand the language of the question. What is an electrophile? Anything which has a positive charge on it is called an electrophile. So where will that positive charge want to attack? Answer this question for me. I'm once again looking at the screen. First answer again, Ratna Kumari is ahead in the race. She is giving me the answer C. Ramakanta is giving me D. Jyochna C. Pradeepa B. Okay, I'm getting mixed answer. D, C, B. I'm getting mixed answers. So this is one of the questions where students have so much of doubt. Okay, but majority of you are correct. Chalo, let us look at that. So first of all, you have to get it attacked by an electrophile. Understand? So where will the positive charge attack most effectively? Where we have a very negative ring, right? Where we have a very negatively charged structure. Now let us look at all these structures. What does Cl have? Let us look at what does the effect of all these groups have. Cl is a Cl is a deactivating group. Understand this thing. This chlorine over here is a deactivating group. Deactivating means what? What is the meaning of this term? This means that it decreases the electron density on the ring. Okay, chlorine is a deactivating group. Similarly, now the competition lies between your phenol and your CH3 group. Now what happens with OH over here? As we just discussed, OH actually participate in the plus R resonance. What does it participate in? Plus R means it gives the lone pair of electrons to the benzene ring, hence increasing the electron density on the ring, right? It is increasing the electron density, doing what? Making the benzene ring electron rich, isn't it? And similarly, what effect does CH3 group have? But just CH3 shows your plus I effect, correct? Now you have to choose between plus I effect, again increases the electron density on the ring, correct? This is also correct. This is also increasing electron density. But when we have to compare between these two, then always remember that resonance effect will always be the dominating effect, right? Resonance effect will be the dominating effect. So the most ring is activated by your OH group, hence C is the correct answer to this. Whoever wrote C is correct, not D bachcha, not D. The answer is C. ठीक है? Chalo. Let us, so this is how the resonating structures are drawn. As you can see, the OH over here is doing what? Increasing the electron density inside the ring, hence making this benzene ring electron rich, so that the electrophile which has a positive charge, this electron ring, benzene ring can attack on that. Okay? So the correct answer is phenol. Now let's move on to the next question. The next question is, a species having carbon with sextet of electrons and can act as an electrophile. Once again, electrophile is what? Anything with a positive charge, isn't it? Isn't it? Now answer this question for me. What do you think is the answer to this? I'm once again looking at the chat box. I'll give you just 30 seconds to answer this question. D. First answer I've gotten D by Ramakanta. Very good. Ratna Kumari. Very good. Joshna. Very good. Very, very good. I've received the correct answer. Sextet of electrons means what? Something which has 6 electrons in it. Understand the language of the question. So what does carbocation have? Carbocation has 3 bonds like this and a positive charge. Correct? So how many electrons does it have? It has 1 electron, 2 electron, 3, 4, 5, 6. So this is a 6 electron rich species. Correct? And is it acting as an electrophile? Something which has a positive charge. Yes, because this is a carbocation. It has a positive charge. It will definitely act as an electrophile, means electron loving species, because it has a positive charge on it. So correct answer is carbocation. So these kind of questions are very, very common. Carbocation, free radical, homolytic, hydrolytic, these basic things, questions are very common, and JEE is returning back to the basic chemistry. I'm once again telling you, please make your basics very, very strong. Correct? Now, let's move on to the next question. The correct stability order of carbocations. Once again, very famous question. Every year this question is asked. Even this year this was asked. So I've attached the very latest format of this question. Every year, same question is asked, right? Some kind of stability question will be asked, definitely. Beta sextet means 6 electrons. Number of electrons is equals to 6. I just explained it to you. Okay, thank you, Mithyas. Chalo, try to answer this thing for me. First answer I've gotten by Ramakanta, once again, C. Okay, everybody's answering C. Very good, very good. Nobody's, okay, very, very good. Chalo, everybody's right in this case. Carbocation means what? But carbocation here has a positive charge on it. Understand? So what will make this positive charge stable? understand one more thing. Whether I am a positive charge or whether I am a negative charge, I am unstable in both of the cases. Only and only neutral species are stable. Understand this. If I am a positive charge, I would want more electron donating species to be attached to me in order for me to become stable. So more the electron donating species, which means more plus I species, right? More plus I species means more stable will be the carbocation. As you can see in the third option, what is happening? It has 3 methyl groups, then it has 2 methyl groups, then it has just 1 methyl group, and this carbocation has no methyl group. Hence, the stability order is the 3 methyl group. The tertiary carbocation is the most stable, then your secondary, then your primary, and then your methyl carbocation. This is the stability order. Again, a very easy, simple question, but asked every year. I will once again tell you another stability order. Right now, this is the very basic thing that I taught you. In your exam, other things can also be asked just like this. Once again, I'm telling you the stability order of carbocations. The most stable carbocation, bacha, most stable carbocation is actually this cation. Understand this thing. This is the most stable in the entire world. This will be the most stable carbocation. The stability of carbocation will also depend on so many factors, but understand another thing, that if any carbocation is aromatic in nature. Can you see that this is aromatic? Why? Because this is following the 6 pi electron rule, which is your Huckel rule, right? All the atoms are sp2 hybridized, so this is an aromatic compound. So all aromatic carbocations or carboanions will be the most stable species in the entire world. Okay? There will be so many orders to quantify which will be the most stable, least stable. So aromatics will be the most stable. Then bacha, what will come after that? After that will come one unique kind of carbocation, just like this. Just like this. Understand the structure of this carbocation. This carbocation is the second most stable carbocation in the entire world. Okay? First stability order goes to the aromatic carbocations. Then this kind of structure of carbocation is the second most stable. There are so many reasons behind its stability, but you just have to remember right now. You don't have to go into the details because nobody knows the mechanism. People call because dancing resonance happen in this structure. There are so many theories, but right now just focus on what is important is the data, right? After that, these two are done. After that, which carbocations are stable? Your phenyl carbocation. For example, this is the carbocation and here is the phenyl ring, here is the phenyl ring, here is the phenyl ring. This is the most stable carbocation. Next is your tertiary carbocation is next in line. So you should understand these things. This is how the stability order of carbocations is followed. If any time it is asked in your exams, you have to give this answer. Correct? Correct? ठीक है बेटा, the dancing resonance, I won't say it is the correct explanation to that. I won't say that because there are many books who deny that claim. So nobody knows, but somehow practically if you look at, then that compound is more stable. Understood? Now let's move on to the next question. Next question is the ascending acidity order of the following hydrogen atoms. See, these kind of questions are asked every year. So I've attached the latest version of these questions because every year similar type of questions are asked. So these are very, very popular type of questions. Acidity order. Acidity means what? Something which can very easily give away H plus, right? That will be the most acidic compound which easily gives away the H plus. Now out of these, which can easily give away the H plus, how will you judge that? You will judge that on the basis of the anion formed. For example, if this H plus goes away, it will leave behind this carbon ion. If this H plus goes away, it will leave behind this carbon ion. Similarly, this carbon ion and similarly this carbon ion, right? Now you have to judge the stability of these carbon ions. So whichever carbon ion will be the most stable species will be the most acidic in nature? Easy? Easy peasy? Chalo. Okay, I've gotten so many order. ABDC, ABDC, CBDA, okay, DBAC. So many different orders I'm getting as answers right now. ABDC seems to be the most common order. Okay, if you have attended my acidity order classes, then you would know. So once again, which carbanion is the most stable? Look at the carbons in all of these cases. Can you see, bacha, that this carbon is actually sp hybridized, right? Similarly, look at this carbon. This is sp2 hybridized, right? Similarly, look at this carbon. This is sp3 hybridized. And this carbon is once again sp3 hybridized. Can everybody see that? Okay? Now I'm going to tell you another order. That is the order of electronegativity. What does that mean? It means which of these is the most electronegative carbon. So as we all know that sp is most electronegative than sp2 and sp3 is the least electronegative carbon. Okay? What does that mean? Understand, like oxygen or fluorine are more electronegative molecules, right? And which charge is more popular on them? Like fluorine has a minus charge on it and it is a stable species, right? So it means that electronegative species can keep a negative charge on them and be stable, okay? So it means that sp carbon will have the negative charge on it will be the most stable, right? So it means the first order is A will be the most acidic species, then will be your B, right? And then will be your, out of these two, both of them are sp3 hybridized, right? Now look at here. Here, three kinds of CH3 are attached. CH3 are what? CH3 groups are plus I group, which means they are giving electrons to this carbanion. What you are doing? I'm already a negative charge. I'm a carbanion. And you're giving me more electrons. You're making me more electronegative. Hence, you're making me more unstable. But I want to be stable. Hence, this is the least stable. Then it will be your D. And then it will be your C. So, this is the correct order. If any of you gave this answer, this is the correct answer. ABDC, correct. Very, very good. Okay, understood the concept. Concept which we use is the order of electronegativity of these species. How do you have to remember it? Like how negative charge is more stable on oxygen or fluorine, which are more electronegative. Similarly, in this case also, negative charge will be more stable on sp carbon because it is a more electronegative carbon. Understood? Let's move on to the next question on your screen. Try to answer this very beautiful question. Which of the following will show geometrical isomerism? Every year, such kind of questions are asked every year. So this question will actually make your fundas very clear. Yes, answer this question for me. Answer this. I'm giving you 30 seconds and then I'll let you know the answer. Yes, I'm looking at the chat box. C. First answer C. Ramakant, Vemi Shetty. Okay, keen vibes. Kavan Kumar. Very good. Okay, Mahirat has said 2 and Ramakant again C. Chalo. Okay, so whatever answer I've received so far are correct. Chalo, let us look at what is geometrical isomerism. Let's start with that. So anything which shows what kind of isomerism, cis-trans isomerism are geometrical isomers, which means what? For example, this is the carbon atom. Between that, there should be a double bond. This is the criteria of it. There should be a double bond, and to this carbon atom, what kind of molecules are attached? For example, if similar molecules A and A are like this, and this is a cis species. This is what? Cis species. And similarly, if similar molecules are opposite to it, this is called a trans species, right? So these are called geometrical isomers. Cis-trans isomerism is geometrical isomerism. Now look at this compound. Can you see? There is a double bond in each case, right? In each case. Now let us look at option number 4 first of all. In option number 4, can you see that here both the atoms are same? H2 here, both the atoms are same, and also there is a symmetry in the compound. This can never show cis-trans isomerism because you need two different atoms for it to show cis-trans isomerism. Similarly, this can also again not show cis-trans isomerism. Similar molecules are there. How can it show cis-trans isomerism, right? Now here these two, between these two, first and second, which can show geometrical isomerism? I know. To this carbon, ma'am, there is a bromine and there is a hydrogen. Okay, understood. But can you see, bacha, if I go from here, whether I go from here or whether I go from here, I get a very symmetrical molecule, right? Whether I go from here, I will draw it for you just to make it a little bit clearer. For example, this is a molecule. This is C, right? One here, H is there. One Br is there. Okay? Here is a double bond. Correct? Now here what is there, bacha? So this kind of structure is there, and here it is a Br structure. So this is the molecule given to you, right? Now, bacha, if I go from here or whether I go from here, I get the same molecule. Hence, this can once again not show cis-trans isomerism. But look at your option number 3. Option number 3, if I try to draw it, it's like C, H here, Br here, a double bond here, right? And a cyclohexane ring, just like this. But can you see that, bacha? The Br is actually here. Now, can you see? Now, can you see that if I go from here and when I go from here, I get Br very quickly. Hence, these are unsymmetrical molecules. Hence, this will definitely show cis-trans isomerism. But this molecule, because it has symmetry in it, can you see there is a symmetry present? Hence, this will not show geometrical isomerism. This will show geometrical isomerism. Is it clear? Clear? Chalo. Chalo, next. The order of relative stability of the contributing structures. Again, important kind of questions. Resonating structures, stability order, very, very important. These kind of questions are again repeated every year. Answer this question for me. Yes, answer was 3. Answer was 3. Now answer this question. Try to answer this question, bacha. I'll give you 30 seconds once again. Beta, chiral carbons are different. Geometrical isomerism you mostly see in alkenes. Alkenes are not chiral. Understand? Chiral carbon are what, bacha? Chiral carbon has to be sp3 hybridized, while your alkene is sp2 hybridized, right? So, alkenes will not show the chiral geometry, the stereochemistry that you want, but your sp3 carbon shows stereoisomerism. Okay? Your alkenes show geometrical isomerism. Okay? Understood? Chalo. Yes, 3 to 1, ABC, ABC, 1, 2, 3, 1, 2, 3, 1, 2, 3. Okay, 3, 1, 2. Okay, I'm getting mixed answers again. Okay, let us look at this question. So, bacha, again, understand one more thing. Whenever we are looking at resonating structures, right? So, the most stable resonating structures will be where there is no separation of charge. Okay? There should be no separation of charge, right? So, where there is no separation of charge, can you see the resonating structure number 1? There is no positive, negative there, right? So, this one is the most stable structure. Now, between second and third, we have to decide which is more stable. So, can you see in second, the negative charge is actually on oxygen. Oxygen, which is a more electronegative molecule. Hence, it can keep a negative charge on itself stable. So, next contributing stable structure is second. Now, the third, can you see there is a positive charge on oxygen, and positive charge on an electronegative atom is not stable. Hence, this is the least stable resonating structure. So, this is the stability order of the resonating structures. Understood this? 1, 2, 3 is the correct order. Very, very good. Chalo, I'm moving on to the next question. The incorrect statement regarding conformations of ethane. Again, very important. Confirmation question is asked every year. There is not even a year where such kind of questions are not asked. This was a beautiful question asked this year. Everything is covered in this question. Try to answer this. Conformations of ethane. Which do you think is the incorrect statement? Again, giving you 30 seconds. 30 seconds. Answer this question for me. Yes. A. First answer I've received is Kavin Kumar A. Mishti has given me C. Sanjay C. Sumanthi C. Very good. So whoever gave me the answer C is absolutely correct. Chalo. So bacha, again, I'm going to show you a very beautiful graph. Can you see this graph here? So these are called the conformation structures, right? These are the conformatory structures of ethane. So can you see, we'll start from here. This is the energy. So as the energy is increasing, it means these are unstable molecules. What are these? Unstable. High energy molecules are unstable. Low energy molecules like this are stable. Understand this thing first, right? So the most unstable is the eclipsed form. Eclipsed form is the most unstable, while the staggered form is what? Where the angles between the atoms, can you see? The angles between the atoms increases by 60 degree, right? Here the angles between in the eclipse format is approximately 0 degrees. There is no angle. It's like right behind the other. In the eclipse form, in the staggered form, they are far apart. When they are far apart, there is no steric hindrance, hence they are more stable species. Correct, bacha? So, eclipse form is the most stable conformation. No, wrong. Eclipse form is the least stable. Staggered form is the most stable. And between staggered, the most stable form is called the anti-form. Remember this thing. Anti-form in the staggered forms are the most stable species. Correct? The dihedral angle in staggered conformation is 60 degree. Yes, we just saw. Can you see a 60 degree angle is there in the staggered conformation? Right? Next is ethane has infinite number of conformations. Yes. If anybody asks you how many conformations there are possible, then the answer is infinite. Why am I saying that? Because, bacha, look at the conformatory structures. Here, the hydrogens in the first structure is right behind the hydrogen over here, right? Now I can increase the angle of the behind hydrogen by 0.1 degree. And then I also have a possibility of increasing the angle by 0.01 or 0.001, 0.02, 0.0002, right? So there are infinite numbers of conformations possible. That is absolutely correct. Next is the conformations of ethane are interconvertible in one another. Yes. Why? Because the energy difference between them is very low. Hence, these are interconvertible species. This is also the correct statement. The only incorrect statement is C. So, the answer is C. Correct? Correct. Let's move on to the next question. Very important again. Every year repeated question. Question is, among the following amines, the strongest Bronsted base. How do you define a base? A base is anything which has lone pair of electrons on it and it can easily give away the electrons. Easily donate electrons. That is called the strongest Bronsted base. Out of these, what do you think is the strongest Bronsted base? I've received answer D by when? Wow. One person has written C. Everybody has written D answer. Very good. Here, bacha, look at the lone pair of electrons on aniline. Here, what is happening? These lone pair of electrons can actually participate in resonance with the benzene ring. Can everybody see that? Because they're participating in resonance. Hence, these electron pair are not available. Is this thing clear to everybody? These electron pair are not available to donate because they are participating in resonance with the ring. Hence, this is not a strong base. Similarly, now let us look at the C structure. Okay? In the C structure, nitrogen will again have lone pair of electrons, right? Now, can you see these lone pair of electrons are again participating in resonance with this ring. Why? because then it becomes a 2 plus 2 plus 2, which it becomes a 6 pi electron system, which means it is becoming aromatic in nature after it is resonating its electron in the ring. Hence, these electrons once again are not available to donate. Not available to donate. Understand this thing. Okay, to donate. Hence, again, not a strong base, not a strong base. Now we are left with two kinds of option. One is NH3 and one is this. Now, bacha, here in D option, can you see that to this ammonia, to this nitrogen, two kinds of alkyl groups are attached, right? Carbon groups are attached, which are alkyl groups. So, alkyl groups are what? These are plus I groups. Everybody agrees to that? These increase the electron density on nitrogen. Hence, the availability of this electron pair on nitrogen is increasing. Hence, this becomes the strongest Bronsted base. Ammonia here becomes weak because it just has hydrogens attached to the nitrogen. Understood this concept? Understood this concept? Okay. Yes. Okay. If we have to compare between B and D, then D is the strongest. Correct? So, I will also write down the order of basicity. So, D is the strongest base, then it is your B. Right? Now, between these two, if you have to tell me, then bacha A and then is your C. So, this is the trend that has to be followed. Okay, this is the trend that has to be followed. This is the basicity trend. Everybody understood? Should I move forward? Chalo. Now, next question on your screen. Which of the following has highly acidic hydrogens? This is favorite questions right now of your examiner. Try to answer this question. I try to include this question in many sessions so that this gets exactly etched in your brains. You'll never do any mistake, because for sure such kind of questions going to be there in your April attempt. Correct? A answer I've gotten. A answered by Raja Lakshmi. Vemi Shetty has answered D. Sumanthi D. Math Lovers 4. Vemi Shetty D. Sambanthan D. Ordinary person D. Very good. I've received many correct answers. So, bacha, its answer is actually D. Right? Again, highly acidic means what? Something which readily gives away H+. Acidic means what? Easily gives away H+. Now, which will be more acidic when after giving, for example, this is the species, right? So, after giving the H+, the anion that is left has to be very stable. So, where that anion is stable, it looks like to me that it is the most stable in the fourth option. Why? For example, here can you see, if the H+ goes away from here, I'll again draw the structure here. There's a C double bond O bond. Here is the CH molecule. Here is the C double bond O molecule once again, and this kind of structure is there, right? Now here the anion will be there after losing the H+. Now can you see both these sides what is present? Electron withdrawing groups, right? This is a very good electron withdrawing group. This is again a very good electron withdrawing group. Again, understand, but a very easy trick is whenever there is any element with a multiple bonds, right? This has multiple bond in it, double bond in it. So any element with a multiple bond will be an electron withdrawing group. So this is a electron withdrawing group, and we want to stabilize this anion. So more the electron withdrawing groups, more stable will be the anion. So this is the most stable. That is why this is the most acidic hydrogen. Understand this part. So the answer is fourth. Correct answer is fourth. Is this thing clear to everybody? Yes. Active methylene. Very good, Sanjay. Called active methylene group. Yes. This is called the active methylene group. Very important for reactions. Chalo. See here in your notes it will be written. Next. This is my favorite question. Tropolone is an aromatic compound and has 8 pi electrons. This is a statement 1 given. Statement 2 is pi electrons of this carbonyl group in tropolone is involved in aromaticity. Now, what is tropolone, ma'am? What are you talking about? Is this even in your course? Yes. This structure is given in your NCRT in your, I guess, hydrocarbons chapter, right? This is a very important structure given in your NCERT like this. This is a tropolone structure. Understand? Understand? Right? Now here the first statement is in tropolone. It has 8 pi electrons. Does it have 8 pi electron? Yes. This is 1 pi electron, 2, 3 and 4. 4 bonds, which means what? 4 into 2 is equals to 8 pi electron species. So this is a true statement. Now it is asking pi electrons of C double bond O group in tropolone participate in aromaticity. So is this group bacha, is this group participating in aromaticity? Understand one more thing. This bond which is outside the ring, can you see? This double bond is outside the ring. This is called the exo bond. This is called the exo bond, right? So whenever, if in a ring you are seeing a exo bond, bacha, try to break that bond. Okay? Try to break that bond. How are you breaking that bond? You are going to break that bond in such a way. Let me make you understand. Okay, 1 second. Yes. So you are going to break that bond in such a way. For example, this bond, the negative charge goes to the oxygen, so the positive charge comes over here. Now look at this structure. Is this the aromatic structure now? So for aromaticity, is it cyclic? Yes. So is it cyclic? Yes. Is it are all the atoms sp2 hybridized? Yes. And the other thing is it following the Huckel's rule? Yes, it is following the 6 pi electron rule. And is it planar in structure? Yes, it is planar in structure. Hence, it is following aromaticity. So, is this pi electron participating in aromaticity? No, because we have developed a positive charge over here. The negative electrons are not participating in aromaticity. So, this statement is false. The above statement is true. This is the how you are going to approach these questions. So, whenever any exo bond is given in your cyclic compound, try to break it. Try to break it. For example, if an exo bond is given over here, like this, and here, like this, a exo bond is given. Now I want you to break this bond. Okay? Now, bacha, there are two possibilities to break this bond. One is, like, if you break this bond in such a way that the negative charge goes over here and the positive charge comes over here. So this is the best way to break this bond, because in this manner, this structure is getting aromaticity. Why is it getting aromaticity, bacha? Can you see that this is a 2 pi electron species? It is becoming aromatic after you're breaking it in such a way that you're giving a positive charge to this carbon and negative charge to this. But if you broke this same bond in another way, for example, if you broke it like this, you gave a negative charge to here and a positive charge to this carbon, what will happen? Now this species become a 4 pi electron species. Can everybody see? And we know 4 pi electron species are anti-aromatic, isn't it? These are anti-aromatic species, hence very, very unstable. So this will not happen. Instead, this will happen. So you have to focus on how to break the bond in order to get that structure which is more stable. Understood this part? Understood this part? Chalo. Chalo. Next, look at this question once again. Among the following compounds, the one which shows highest dipole moment. This uses the same concept which I explained to you just now. Highest dipole moment. Try to answer this question. Try to answer this question for me. Yes, I'm giving you 30 seconds. This uses the same concept that I explained it to you. Can you see that there is a presence of an exo bond in almost every situation? Try to break this bond in such a manner that both of the species get aromatic nature, right? So whichever will be the most aromatic species, right? That will has the highest dipole moment, right? Correct. First answer I've gotten is by Sanjay 1, Prasad 1, very good. Game over Tamil 1, Revantha A. Wow, love. Okay, sorry. ठीक है. Lovely students, lovely. You're all on the right track right now. ठीक है, all on the right track. So look at the number one molecule. If I try to break this exo bond, what can I do? I can do one thing. I can give this the negative charge and this carbon the positive charge, right? If I broke it like this, can you see that this has now become a 2 pi electron species, right? This has become the 2 pi electron species. Similarly, this has become a 6 pi. Can everybody see? 2 plus a lone pair of electron. So this is a 6 pi electron species now. So both of them are aromatic in nature, 2 and 6, right? Following the Huckel's rule. So therefore, this is the aromatic compound. Hence, this will have the highest dipole moment. Why is that the case? Because I want to become an aromatic compound, right? So that is why I will develop these charges as soon as I can. I will not stay a double bond. I will instead develop a positive negative charge because that is helping me to become an aromatic compound. Hence, I will be the most dipolic in nature. Okay? Chalo, next question. Understood? Understand the concepts here. Now, the next question over here. Again, which of the following is the correct hydride affinity order of carbocations? We just now I told you the correct order of stability of carbocations, right? Okay, we just discussed the stability. Now, based on that, hydride affinity means what? That the affinity means what? To love hydrogen. If I'm a carbocation, if I'm very stable carbocation, would I want to accept any more hydrogen in me? Why would I want to accept? I'm already stable. I don't want anything inside me anymore. I'm stable. I don't want you. Okay? So whichever carbocation will be the most stable will have the least hydride affinity. Understand that. If I'm more stable, I want to remain that way. I don't want to change myself. The least stable. So here you have to let me know which is the least stable carbocation. Answer that question for me. Answer that question for me. CBDA. Okay. Okay, D. Very good, very good. So here in the cases I just explained that this kind of carbocation out of dancing resonance or whatever, some reason this is a very, very stable carbocation, right? So see, I'm first of all writing down the stability order of carbocations, right? So here C is the most stable, okay? Then can you see in B there are so many phenyl rings there, huh? Phenyl makes the carbocation stable because in phenyl rings it can resonate again. So then the B, okay? Next come your tertiary carbocation, then your D, and then it is your allylic. Okay, this is not even allylic, this is a primary carbocation. Then it comes your A. So this is the stability order of carbocation. Hence, hydride affinity order. Hydride affinity order. Hydride affinity will be exact opposite of it. So C will be the least, then B, then D, and A will have the highest affinity order. So A here, this is the correct hydride affinity order. If I'm stable, I don't want to accept any more hydrogen inside of me. Correct? Chalo. Yes, CBDA. Very, very good. Proud of you students. Chalo. Next. Okay. Here, that was just, you can use it as a PDF file. Okay, next question. The descending order of acidity of the following carboxylic acid is. We'll directly move on to the questions because I've already explained it to you. If I'm aromatic, I'll be more stable carbocation. That was the only thing written in that slide. Right? The descending order of acidity of the following carboxylic acid. Once again, acidity means what? Which easily gives away the H plus. How can you judge that? Like after losing the H plus, the anion formed. After losing the H plus, the anion formed. The anion formed. The anion formed. The anion formed. Right? So it depends upon the stability of the carbanion. Whichever carbanion is more stable, that will be the most acidic order. Very good. I'm getting very many answers. BDCA, BDCA, BDCEA are the, okay, okay, okay. Chalo, chalo. Now let us look at the stability of carbanion. If I am a negative charge, what kind of species do I want on me? I want those species which take away the electrons from me, right? I'm negative. I want those which have a minus I effect. So out of these, the biggest minus I effect is shown by fluorine, and there are 3 fluorines attached. So B bacha is the most stable carbocation. Okay? So it depends upon the minus I effect order, and minus I order is like this: fluorine, chlorine, bromine, and then iodine. Understand this. This is the minus I effect. Like fluorine is the most electronegative element. So it will take electron towards itself more strongly, right? So B will be the most stable. Then it will be your D, right? Then it will be your E. Then it will be your C. Then it will be your A. Correct? Here CH3 is actually a plus I group. Plus I means it is donating electrons. I'm already negative and CH3 is donating me more electrons. So this is the most unstable anion. Hence the least acidic. Most acidic is B. Okay. So this is the order followed. Everybody understood? Correct, correct, correct. Chalo. Next question on your screen. Now we are talking about the basicity strength. Very important. Every year this question is asked from the amines chapter. You need to know the basicity trend of both amines, both kinds of amines, right? So the correct order in aqueous medium, whenever we are talking about the basicity in aqueous medium, then so many effects take into place. The solvation effect, right? The hydration effect, the hydrogen bonding, the steric hindrance. There are 4 kinds of effect participating in whenever we're talking about the aqueous medium basicity of amines. Okay, so this order is given in your NCERT, and that same order is asked every year. Every year, I'm telling you, very, very important. Answer this question for me now. So the first answer I've gotten is by Sanjay, then Sambanthan C, Sanjay C, Rajalakshmi C, B. Okay, different answer, different answer. Beta, it is not wrong at all, not wrong at all. Understand the concept. Chalo. So, bacha, this is after I told you in amines there are so many effects into place. There is a steric hindrance effect, there is a hydration effect, solvation effect, hydrogen bonding effect, right? So, all these effects have to be taken into consideration. We're talking about the stability of amines. So, understand that secondary amines are the most basic. Secondary amines are the most basic in aqueous medium, whether a methyl group is attached or the ethyl group is attached to the nitrogens, right? So this is the order. When to the nitrogen, ethyl group is attached, secondary amine is the most stable. Then is your tertiary amines, then it is your primary amine, and then it is your ammonia. Okay? Similarly, basicity order, when methyl group is attached, again secondary amines are the most basic, then is your primary amine, then is your tertiary amine, and then it is your plain ammonia. So this is a very, very important order. Understand. So when to the nitrogen, ethyl is attached, what will be the order? When to the nitrogen, methyl group is attached, this will be the order, right? Understand, I have given you both the orders. Only from this the question comes, from nowhere else they ask. ठीक है? Chalo. Next, I'll try to answer this question. Which will undergo deprotonation? Deprotonation means what? I am taking out the proton. That is once again acidity, right? That is, you are taking out minus H plus. You're again taking out the H plus ion most readily in the basic medium, which will give out the H plus most easily. Once again, it depends upon the kind of anion formed after I've taken out the H plus, isn't it? So let us understand the A. Here the anion formed will be here. Here the anion formed will be here. And here the anion formed will be here. Right? After the H plus goes away. Right? Now answer to me, which of these is the most stable? Right? Yes. So which will undergo deprotonation most easily? where this negative charge is the most stabilized. Correct? So answer I have received A, 3, 1, 4, B. Okay. Various answers I am receiving. Various answers. I am going to tell you how to approach this question. Okay. First of all, look at the C option over here. So we are going to talk about C. So can you see that this O-methoxy group over here, है ना? What can this do? This can actually undergo resonance with this oxygen atom like this. Is everybody agreeing to that? This can undergo resonance with this structure, right? Similarly, what this negative charge will do? This negative charge will again want to go into resonance with this oxygen. But can you see that this oxygen is already getting occupied by the resonating structures of OMe. Hence, this negative charge is actually getting lesser chance to stabilize itself through resonance because this methoxy group is already participating, it is already occupying that oxygen for resonance. Hence, this negative charge is getting a lesser chance. Similarly, here, there are two methoxy groups, right? So, here once again, both of these methoxy groups are doing what? Using this for resonance once again. So, this negative charge is getting a lesser chance to make itself stable through resonance. But in the A option, what is happening? I'm again drawing the A option over here. A option, this is the negative charge over here, and this is over here, this is over here, right? Now to stabilize this negative charge, this will undergo resonating structures with both the oxygen atoms, right? Without any competition. There is no methoxy groups here to cause competition. Hence, this will be the most stable carbon ion. Hence, this compound will be like, yeah, you take away my hydrogen. I don't want it because I'm very, very stable without the hydrogen. So, I will undergo deprotonation very, very easily. So, the answer is A. Correct? The answer is A. Understood? Hi, bacha. A. Did everybody understand this reason? Just let me know that. Just let me know that. Everybody understood this reason, right? Yes. Chalo. Look at this once again. This is again a very important kind of question, basic chemistry question. Try to answer this. Try to answer this. Which of these is a Spiro compound, is an aromatic compound, is a non-planar heterocyclic compound, and which one is a bicyclo compound, right? So, I'm going to tell you one more thing. Bacha, whenever, look at the C compound. In C compound, can you see that through that two carbon chains, two cycles of carbons are attached through only one carbon, right? This kind of attachment is called a Spiro compound, okay? When only through one carbon there is attachment. But when two cycles are linked through two carbons like this, then it is a bicyclo compound, right? Okay? And I know very well that you can identify what is a aromatic compound, what is a, so this one will be the aromatic because the oxygens lone pair will participate in the Huckel rule structure. So this is once again a 6 pi electron system, right? And this is a plain, non-planar heterocyclic compound. Okay? Chalo. Yes. ठीक है? I'm moving on to the next question. It was an easy question. Just understand what is a Spiro compound, what is a bicyclic compound. Once again, we have a question for among the following marked protons, of which compound shows the lowest pKa value. So can you see such kind of questions are repetitive, repeating, right? Try to answer this question for me, which shows the lowest pKa. pKa and acidity have an inverse relationship. pKa is inversely proportional to acidity, which means lowest pKa means highest acidity order. Correct? Try to answer this question for me. You've seen this question, very good. Then attempt, bacha. Attempt. Chalo. See these questions. See. Very, very good. Very, very good. So again, bacha, what is happening here? Acidity, which means what? Which can easily give away the H plus ions, right? For example, if I take out the H plus from here, I will be left with a negative charge here. again a negative charge on this carbon, here again a negative charge, and here again a negative charge. Okay, understood this? Now bacha, if you have to compare where there is a benzene ring and where there is an absence of benzene ring, right? Can you see in both of these cases we're actually getting benzylic anion, and benzene bacha has a very good, benzene is known as a very good electron withdrawing group. Understand this thing. Benzene makes a very good electron withdrawing group. So these carbon ion automatically in these two situations are more stable than the above two situations. So we are going to cancel them out automatically. Now we have to compare between these two. So here the benzene rings are the same on both sides. What is changing? Here the substituent is OH. Here there is CH3. Now let us compare their qualities. CH3 is what? CH3 has a plus I effect. That is it. It is not interfering in anything else. But OH over here, can you see OH? The lone pairs of this will participate in resonance with this oxygen, right? And this negative charge, how will it stabilize? By undergoing resonance with this oxygen, with this electron withdrawing group. So can you see that this OH is actually hindering the resonating capacity of this negative charge, right? Because it is taking up the participation of this double bond O, right? So therefore, but this CH3 is not using this double bond O in any resonating structures. Hence, this compound will be the most stable compound. So the answer is C. Correct? Understood this part? What this OH is doing? OH is taking up that double bond O itself for resonance. Hence, this negative charge is getting less chance to resonate itself. Hence, this negative charge is less stable. But here, the negative charge will be more stable because this double bond O is not getting used by any other molecule for resonance. There is no competition here, but there is a competition here. So, among these two, this will be the most stable species. So, the answer is C. Yes, very good. Chalo. Next. Okay, try to answer this question for me. You have two assertions and reasons given to you. I will not answer this. You are going to answer this for me. Is the assertion true and is the reason true? Answer that much. True, false, true, false. Answer that to me. Assertion is 6 annuline. This is a 6 annuline. 6 means what? Number of electrons. This has 6 pi electrons. This has 8 pi electrons. And this has 10 pi electrons. Right? So it is telling you, are they respectively aromatic, not aromatic, and aromatic compounds? Is this thing right? So my answer is, this is a benzene ring. This is definitely a aromatic compound. Yes. Okay. This is annuline. 8 pi electrons. You say, ma'am, 8 pi electrons, which means what? Ma'am, this should have been the anti-aromatic compound. Why? Because it is following the 4n pi electron rule, because it has 8 electron species in it, isn't it? But this is not anti-aromatic compound. This is not anti-aromatic, even though it is following the 4n pi electron rule. Why? Because this species, bacha, actually is not planar and gets a tub-shaped structure just like this. This species is non-planar species. Hence, this is actually a non-aromatic compound. Right? Anything which loses its planarity is actually a non-aromatic compound. Similarly, this structure, look at this, is a very famous example, important example. Here, once again, you will argue, ma'am, this has 1, 2, 3, 4, 5. This is a 10 pi electron system. So, ma'am, this is following the 4n plus 2 pi electron rule, which is your Huckel rule. This is following that. Then, ma'am, this should be a aromatic compound. But once again, due to these hydrogens over here, can you see? These hydrogens cause steric hindrance. And due to that steric hindrance, this molecule loses its planarity. This is once again non-planar molecule. Hence, this is also a non-aromatic compound. So, both of them are non-aromatic compounds. Is this clear? Only benzene is aromatic. The other two are non-aromatic because they are losing their planar structure. Okay? Yes. Assertion is false. Very good. This is false. Now, reason is planarity is one of the requirements of aromatic system. This is true, right? Planarity is one of the requirements. For any system to be aromatic, it needs to be planar. There are 4 conditions for aromatic system. One is it should be cyclic. Next is every atom in that cycle should be sp2 hybridized. Number 3, it should follow the Huckel rule. Number 4, that it should be planar structure. Understand, these 4 conditions are necessary for aromaticity, right? Now I'm moving on to the next question. Yes, B is true, the A is false, correct. Chalo. So this is again for your understanding. I have explained it. You can get it in the PDF. I will move to the next. Again, acidic strength, very, very important kinds of question. Answer this very easy for you guys now. Arrange the following in decreasing acidic strength. Acidic strength means what? Which easily gives away the H plus, right? Now, nobody should do this wrong. Which easily gives away the H plus. H plus is gone, H plus is gone, H plus is gone, right? And what is left behind? The anion. Now we will check the stability of these anion, isn't it? We will check the stability of this anion, right? Yes. ABCD. ABCD. Sanjay has given me the answer ABCD. Chalo. More answer is ABDC by Sai Sarika. Naga Arjun has also given me ABDC. Sanjay has given me ABCD. Chalo. Let us see what is happening. Now, to see which is the most stable, to see which is the most acidic over this molecule over here, what we have to see over here, bacha, the stability of the anion, the NO2 here. What effect is it exerting? The NO2 at the para position exerts 2 kinds of effect, which is the minus I effect plus your minus R effect, isn't it? Minus I, minus inductive, it is taking away the electrons, electron withdrawing group, and minus R, it is through resonance also it is taking away the electrons. It's showing 2 kinds of things. It is taking away the electrons, hence making the negative charge very, very stable. Hence here, NO2 over here, this only and only shows minus I effect. Understand another thing. At the meta position, only inductive effect will be shown. Resonance effect will never be shown at the meta position, right? Only inductive effects will be shown. Similarly, OCH3 over here. OCH3 once again here shows the minus I effect. Okay? If you want to argue with me, ma'am, OCH3 shows plus I effect, I will say no. Oxygen is a more electronegative molecule. It has a tendency to take electrons towards itself. So it shows minus I effect. Understand this thing. Okay? Don't argue with me on that, because this is bacha the correct inductive effect. Okay? Now here OCH3 at the para position shows 2 kinds of effect. Minus I as well as plus R. Right? What it is doing, bacha? It is increasing the electron density in the ring. The lone pair of electrons on OCH3 increasing the electron density, hence making the ring electron rich. I already have a negative charge on me and you're giving me more electrons. Hence this will be the most unstable species. Okay? Unstable, hence least acidic. So the most acidic here is A. Most acidic is A. Now between these two we have to choose. Between 2 minus I effect, then bacha NO2 has a more prominent minus I effect than the OCH3. So it should be B, then it should be C, and then it should be D. So ABCD is the order. Whoever gave the answer ABCD is right. Correct. Not ABDC. It is ABCD because it is increasing. Can you see? The last OCH3 is giving electrons through resonance to the ring. Hence increasing. Hence it is making the ring electron rich. Hence destabilizing the negative charge. To stabilize the, if I am negative, I want more groups that are taking away electrons from me, right? Not giving me electrons. So this is the correct order. This is the correct order. Yes. Let's move on to the next question. Again, your favorite question. I attached some basic simple questions so that you guys also can relax in the middle. Answer this question for me. Which of the following structures is aromatic? Okay, what are the conditions? Number 1 should be cyclic in nature. Number 2, every atom should be sp2 hybridized. Number 3, it should follow the 4n plus 2 pi electron rule, right? Number 4, that it should be planar structure. So which of these compounds are aromatic in nature? First answer I've gotten by Sanjay is saying 2. Very good. Game over Tamil, B. Very good. Sanjay, A and B. Very good. Vemi Shetty, very good, very good. IT Bombay. Hi, IT Bombay. After so much time, we're meeting again. Hi. Chalo. The correct answer is B. Only in these two, it is following all of these rules. The Huckel's rule, can you see? In A, it is a 6 pi electron system. This is once again a 6 pi electron system. This C, on the other hand, is a 8 pi electron system. This is anti-aromatic. And this one is once again 1, 2, 3, 4. This is once again a 8 pi electron system. Again, anti-aromatic. Only A and B are aromatic. The other two are anti-aromatic species. That is very unstable. Very, very unstable. If you want to know the stability order, it is aromatic. Aromatics are the most stable in the entire organic chemistry. Then are your non-aromatics, non-aromatic, and at the end will be your anti-aromatic molecules. Okay? This is a stability order. Anti-aromatics are the least stable. Aromatic most then non-aromatic, then anti-aromatics. Chalo. Okay? Shall we move on to the next question? This is my favorite question once again. See, nucleophilicity order is asked. The correct order of nucleophilicity, I love this question. So many concepts will be clear to answer so many different kind of questions. Electrophilic substitution question, nucleophilic substitution question. So many questions will become easy if you understand this concept. Try to do this question. I'm giving you 30 seconds and then I'll explain. Nucleophilicity. Nucleophile is what? Anything which has a negative charge on it is a nucleophile. So whichever has the highest capacity to donate electrons, okay, to donate electrons easily. So whichever donates the electrons easily has the highest nucleophilicity. Simple. So what do you think is the answer to this? First answer I've received by Sanjay is D. Then cricketer D. Chandra has answered A. Game over Tamil D. Okay, A, D, D. Okay, D, D. Many people have answered me correctly. Very, very good. Chalo, let us look at the order number A. I'll explain it to you one by one. Here fluorine and OH minus are given to you. Right? Now it is saying that fluorine has more nucleophilicity. It means donation of electrons. Now understand one more thing. Between fluorine and oxygen, which one is more electronegative? Isn't it fluorine? Fluorine is more electronegative, meaning what? It will hold the electrons more closely and will not give them away. So between these two, actually, OH is more nucleophilic. Hence, this is the wrong trend given over here. OH minus is more nucleophilic. It will easily give away the electrons because it is less electronegative. Correct? In option number B, once again, this is a OH minus species over here. So whichever has a negative charge on it will obviously give away electrons easier than a neutral species. H2O is neutral. So this has a negative charge. Here once again, OH minus is more nucleophilic. Give away, donate electrons easily. Then H2O, hence wrong trend given once again. Now look at C. Same thing. Again a negative charge will give away the electrons easily. Hence once again wrong trend. But here the negative charge over here, this is the right trend given. So D is the correct answer. Okay? So if I have a negative charge on myself, I will obviously give the electrons easily. Okay? D. Correct answer is D. Now the compounds which show significant intermolecular hydrogen bonding are. Who will answer this question for me? I'm again looking at the chat box. Giving you 30 seconds. 30 seconds to answer this question. Intermolecular, understand, inter means between two molecules. between 1 and 2 intermolecules which will show most H bonding? A, B or C? First answer I've received by Ritik is A. And then C. And then A. And then Rajalakshmi has given me the correct answer. First correct answer received by Rajalakshmi Raiji. B. Sanjay also given me, keen vibes are given me B. Very good. So whoever has answered B is correct. Bacha, in A, what will happen? In A, bacha, there will be hydrogen bonding between among the molecule itself. So this actually shows intramolecular. Intramolecular. Intra means what? Within the same molecule, it is showing H bonding. Okay? Similarly, look at the C option. In C, there is so much steric hindrance. Can you see? There's a big alkyl group here, big alkyl group there, big alkyl group here. So therefore, due to steric hindrance, this does not show much hydrogen bonding due to steric hindrance. Right? Hydrogen bonding is not shown that much. But in B option, bacha, can you see? Even this NH can show intermolecular hydrogen bonding and even this OH, right? So there are two options to show hydrogen bonding. So B is the correct. So inter between two molecules, this will show the most H bonding. Okay? A shows the most intra within itself the hydrogen bonding. B, very good, very good. Understood? You should understand the reason because similar question will not be repeated but concept can be repeated. Hai na? Chalo, the number of stereoisomers possible for 1,2-dimethyl cyclopropane is. Focus on the word stereo. Stereoisomerism they have asked. So answer this question for me. 1,2-dimethyl cyclopropane. Who can answer this question for me? Hi. Answer this question for me. I'm giving you 30 seconds. 30 seconds. Looking at the chat box, you know what you have to do. Just take out your notebook and try to draw the structure and tell me the answer to this. Can you please again explain intramolecular? C answer I've received by Pradeep, Sanjay, C. Okay, all of you are wrong. Congratulations on that. You are very wrong. What is the structure of cyclopropane? First of all, I'll draw a cyclopropane. A cyclopropane looks like this. Okay? 1,2-dimethyl cyclopropane. 1,2 means what? On number 1, there is a methyl group like this. On number 2, there is a methyl group like this, which means there's a hydrogen here, there's a hydrogen here. So this is one isomer. The other, this is the cis isomer. Okay? But there can also be a trans isomer, isn't it? Because this is a cyclopropane. So the CH3 can be here. In the other case, the CH3 can be here. The H is here. The H is here. Right? These two, cis and trans. Okay, everybody got it. But can you see that this trans isomer can also have an enantiomer, isn't it? Can also have an enantiomer just like this. The CH3 is here. The H is here, the H is here and the CH3 is here. Can you see that this can also have a enantiomer? Hence, the answer is actually D. 3i, stereo, because it has specifically mentioned stereoisomer, not symmetrical. Stereo means you have to take into account the enantiomers. Why will the cis isomer not have an enantiomer? Because they have a plane of symmetry. Can everybody see? A POS is present. And whenever any symmetry is present, then that kind of molecule will never show stereoisomerism. Only other kind of molecule just like this can show stereoisomerism. And this will not have the diagonal symmetry because the cyclopropane is a very strained molecule. Okay? So there is least presence of diagonal symmetry in here. So it actually shows an enantiomeric pair. So the answer is D. Okay? Chalo. Let us move on to the next question. Next question, the correct stability order of the given carbocations. We have done a very similar question. See, that's what I'm telling you. This is a question from 2021. 2021 repeated. Even this year this was asked. In 2023 it was asked. 2022, 2021. Every year this question is asked. Now answer this question for me. We have already learned the concept. Carbocation stability. Where will the positive charge be more stable? Answer this question for me. I'm looking at the chat box. First answer I've received by Sanjay is ADBC. Okay, Sanjay, I will look at your answer. Okay, anybody else other than Sanjay want to answer? Rama Krishna has answered DABC. Okay. Okay, anybody else? I've already received a contradictory answer. Then ACBD. Okay, different answers I'm getting by Gayatri Devi. I'm getting a different answer. Chalo. ADBC. Chalo. ADBC seems to be the most common answer. So we are talking at the stability of the carbocation. Okay? So we all know that this is a benzylic. Can everybody see? This is a benzylic carbocation. And benzylic, whether it is a benzylic carbocation, whether it is a benzylic carbanion, both of these species are very, very stable. Why? Due to resonance. This can go over here and it can stabilize the positive charge. So the most stable is benzylic. A is the correct. Then between B, C, D. Now let us compare the hybridization of carbon. Here the carbon is sp2 hybridized. Here the carbon is sp3 hybridized. Here the carbon is sp hybridized. Now we know that sp is the most electronegative carbon, right? Electronegative, you immediately have to think about a fluorine atom or oxygen atom. Which is more electronegative? Fluorine. So, have you ever seen a positive charge on a fluorine atom? Have you ever seen a positive charge stable on a fluorine atom? No, because fluorine is more electronegative. Hence, only and only a negative charge is stable on fluorine. In the similar manner, a positive charge will be least stable on sp hybridized. So, the correct answer is A, C, then B, and then D. So, whoever answered this is the correct. A, C, B, D. IIT Bombay, right. IIT Bombay, right. Sanjay, right. Correct. Pola, right. Correct. I'm looking at the answer. Yes. So, this is the final. So, because electronegativity trend is sp is the most electronegative carbon, then sp2 and then your sp3. ठीक है? Understood this? Chalo. Next, this question. Which among the following resonating structures is not correct? This is going to test your basics of chemistry. Basics of chemistry. Answer this question. I'm giving you 30 seconds once again. Then I'm going to tell you the answer to this. Basic. Just dive into the basics of chemistry. What do you think is the answer to this? Yes, answer this question for me. Answer this question for me. Looking at the chat box. You got it. Very good. 3. First answer I've received is 3 by G1's Art. By Maheshwaran. Then Sanjay has answered C. Okay. Mishti has answered A. Mishti has been giving me the correct answers. Very, very good, Mishti. Keen vibes. Right now, most of the people are wrong. Only Mishti, Abhi, and Mishti once again is right. Okay? Look at the very, very first option. Can you not see that here the positive charge are on the just like right opposite to each other, right next to each other. There are 2 positive charges. Can 2 positive charges be right next to each other? No, because they'll repel. So this is the most unstable species. So this is the not correct version because 2 positive charges can never remain together. Can you see? They are exactly next to each other. So this is the most unstable species. Right? 2 positive charges, 2 negative charges, 2 similar charges can never be next to each other. Never ever be because they cause so much repulsion. So this is the wrong resonating structure. Understood? I'm moving on to the next question. Now we have entered the den of so many reagents. Very, very important. These are some of the basic reagents asked every year. These reagent chemistry you must definitely know. Otherwise, we will make it strong in this session by solving so many questions. the question number 1 on your screen and try to answer this. Then I'll tell you what the correct answer is. ठीक है? Okay, Mohammed Yusuf. Try to answer this. So you have a question on the screen, right? You have an alkene and you're trying to react that alkene to form two kinds of products. One is with H plus H2O. The next is with B2H6. A and B products. What do you think is the right answer to that? What do you think is the right answer? Beta, where nitrogen was making 5 bonds. Let me go back. Abhishek is questioning me something. Which bacha, where 5 bonds? This one. This one, right? Yeah. But bacha, if you want to compare, right, nitrogen actually shows a +5 oxidation state if you go to your P block chemistry, right? So this is somewhat possible, but that is never possible if you have to compare and give just one answer. So answer this question for me, guys. Answer this question for me. Answer this question for me, everybody. D. Okay. So let us look at all these reagents. So in the number first, the A reagent that you have been given is H plus and H2O. What do they do? We have to attach H2O molecule on one. So here H plus and H2 actually shows what? It actually goes through the carbocation mechanism, isn't it? So the molecule given to you is this kind of alkene, right? Here is the CH3 present and I'm trying to react it with H plus and H2O. So where will the OH attach? So OH will attach on the most stable carbocation and also rearrangement happens in this case, right? Remember with H plus H2O, it is a carbocationic mechanism, hence rearrangement will definitely take place. But in this situation, there is no possibility of rearrangement. So the answer is what, bacha? So the answer will be here will be the CH3, here will be the OH and here will be your H. Okay? But with B2H6, what happens? B2H6, you get an anti-Markovnikov product. What do you get? You get an anti-Markovnikov product. Here you get the OH, here you get the H, right? So you get with the B2H6, you're getting the anti-Markovnikov product, right? But with H plus and H2O, you get the Markovnikov product. Is this thing clear to everybody? Yes, so the correct answer is actually your, not B, bacha, your A option is D. The correct answer is D. A and B. Okay, the correct answer is D. Chalo. I'm moving on to the next question. Once again, we have another kind of alkene and two kind of reagents to attach OH and H. One is again BH3, which is hydroboration oxidation. The another one is oxymercuration and demercuration reagent. Once again, try to answer this question for me and then I'll let you know the answer. What do you think is the answer to this? Try attempting this. What happens with oxymercuration, demercuration reagent? We just talked about this, right? Here again, what happens? The addition is according to the Markovnikov rule, but there is no rearrangement possible, right? In H plus and H2O, you get a carbocationic mechanism, hence rearrangement of the carbocation was possible. Here, according to Markovnikov, the OH gets attached, but there is no rearrangement possible. Similarly, no rearrangement is possible even in borodine and only anti-Markovnikov product you get. So now answer the question for me. First answer is given by it's Jen, B. So many B's I'm getting by Maheshwaran, ordinary person, B, Mahirat. Okay, very good. So the correct answer is the A option is the anti-Markovnikov product and the B option is that. Very good. Okay, should I move on to the next question? The next question is, in the following given reaction A is, what do you think should be the A product? So you have these many options in your screen. So what will happen? You are trying to react this alkene with HBr and you want to form a product. What will happen in this case? Remember, this is a cyclobutane given. So it can undergo ring expansion, right? So what will be the answer to this question? Try to answer this question. I'm giving you 30 seconds once again. Yes, try to answer this question for me. B. I'm looking at the chat box. नहीं बच्चा, आपसे क्यों फाइट होगा मेरा? A. Remy Shetty A. Maheshwaran A. Nikhil Yadav D. Sanjay 4. Okay, 1, 4 D. Okay, I'm getting mixed answers right now. Let us look at this question. So the compound given to you is this kind of cyclobutane with a double bond over here and a CH3 over here, and you're trying to react it with HBr, isn't it? So the HBr can actually break down, understand the very basics of chemistry. This will break down into H plus and Br minus, isn't it? Now we know that here a double bond is present. A double bond is electron rich, hence it will attack your H plus over here. So what will be the next step? This is once again cyclobutane over here. This is C, this is C. So the H will get attached over here, right? Here will be the CH3 once again, and the positive charge will come over here. Why did the positive charge come over here? Because this is a tertiary carbocation. Can everybody see that? Now I'm going to tell you another thing. Now ring expansion will happen. What is ring expansion? Can you see that this is a box? This is a dabba given over here. This box will open up and will try to attach to this carbocation. The next step will be that this will form actually a 5-membered ring just like this. The positive charge will come over here. The CH3 is over here. And here once again the C molecule again. 2 methyl groups are over here. Okay? Now bacha, there's a positive charge over here. The next thing that could happen could be a 1,2 methyl shift, isn't it? 1,2 methyl shift can happen in this case right now. This positive charge can move over here to become a tertiary carbocation. Right now this is a secondary carbocation. Hence what can happen? This can move like this. This can be a positive charge over here and the methyl group then moves over here by 1,2 methyl shift. 1,2 methyl shift happens. Okay? And then what will happen? This Br minus now attacks this positive charge. Hence the final product that you're getting is a cyclopentane like this with a Br over here and 2 methyl groups over here. So this is the correct answer. Everybody understood the correct answer? Everybody understood the correct answer? Okay? Now let us see where this answer is given to us. I think this is given to us in the 4th option. So the answer 4 is correct. Whoever gave the 4th answer is correct. This is the correct answer to that. 4th. Very, very good. I've received so many correct answers. Proud of you. Proud of you. Okay? Chalo. Next. In the given reaction, identify A and B. So you have a reaction. You are reacting hydrogen with A compound in presence of palladium and carbon, and you're getting this kind of alkene. Okay? As we know, hydrogen and palladium. So whenever you are hydrogenation, what you are doing in this reaction? In the first reaction, doing hydrogenation. In the presence of palladium and carbon, the hydrogenation that happens is a syn reaction. Syn means what? Both the hydrogens get added from the similar side, either from the below or from the top. Can you see? Both hydrogens got added on the same side of the double bond, right? Now look at this triple bond over here. Now what you're doing, now you want to answer what is the B product over here. So you need to answer me what is A and what is B. What is the function of sodium and liquid ammonia? This is again doing your hydrogenation, adding hydrogen. But here the addition of hydrogen is actually anti. What kind of addition? Anti. So one hydrogen will come from below, the other from above. Hence, how will the hydrogens add? If one comes from here, the other will come from here. And this will get converted into a double bond, butene. Right? Now answer this question for me. Now answer this question for me. B, 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 D. Okay, I'm looking at the answers. I've not received the correct answer yet. So the first is, bacha, first will be a pentyne. Will it be a 2-pentyne? 1, 2, 3, 4. ठीक है, 2-pentyne, ठीक है, ठीक है. And last will be your trans-2-butene, not cis-2-butene. Trans-2-butene. So the correct answer is, I just told you that the two hydrogens are adding from the opposite sides. Hence, this is forming a trans structure, isn't it? Two similar things are on the opposite end. Hence, you are forming a trans-2-butene. The correct answer is trans-2-butene. D, correct, correct, correct. I'm moving on to the next question. Again, what you are learning through this, you're learning 2 methods of stereochemistry. Now look at this reaction. Major product of the following reaction is, again, an alkene is given and you're trying to react that alkene with DCl. DCl means what? D is the deuterium. Isotope of hydrogen is used over here. How can you solve this question? Yes. Yes, trans will be the product. Yes, Vishnoi Gupta. Yes, Karthik Vishnoi Gupta. The great Karthik. Oh my God. What do you guys do on the internet? Chalo. D. D. Very good. Very good. First answer received by cricketer Sun 28. D. 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 Sai Sarika C. D. 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 Okay. Very good. The correct answer is actually D. What is happening? This kind of alkene is given to you. This kind of alkene is given, right? Here the CH3 is present and here DCl you're trying to react. So this reaction, bacha, with HCl or DCl is actually once again a anti-addition. Anti-addition, which means if hydrogen comes from below, the chlorine will come from the above. Okay? So the correct answer will be, first of all, what will happen? First of all, like this, the CH3 is here. So first of all, the deuterium will get added and a positive charge will develop over here, right? A positive charge. So the D will add over here, isn't it? Now, bacha, what will happen? What will happen? So the D will actually come, one second. Yes, so the D will attach over here and now this chlorine can attack on this positive charge. So the correct answer looks like this. This is D, this is Cl, this is CH3, this is H. So this is the correct answer. Okay? Everybody got it? So the correct answer is D. Once again, anti-addition. Anti-addition of HCl. Okay? Chalo. Next, identify the product A and B. You have been given an alkene. Trying to react it with Cl2 in 2 conditions. Number 1 condition, in presence of light. Number 2, in presence of CCl4. Both the cases, different kind of additions happen. Tell me what can be the answer to this. I'm giving you 30 seconds once again. 30 seconds once again. Hi, bacha. Try to answer this question for me. Try to answer this question. I'm looking at the chat box. I am looking at the chat box. A. Nikhil Yadav has answered A. Chandrakala A. Oh, so much A answer. Hi, Vedantu KRD. Okay. Hi, Gayatri Devi. A. Wow, so many people have answered A. Very good. So, bacha, here, how do you approach it? I'll again tell for the students who do not know. So this is the alkene. So we are trying to react it with Cl2. What will happen if I react with Cl2 in presence of light? In presence of light, bacha, allylic addition happens. Allylic means at the allylic position. So allylic is, this position is allylic. This is also allylic position. So what will happen? What will happen? The alkene will remain as such. At both the allylic positions, chlorine will get attached. Similarly, if you are trying to react the Cl2 with in presence of CCl4. CCl4, what happens? Direct addition on the double bond happens, right? So direct addition on the double bond happens. So here the Cl, here will be another Cl molecule. Okay? So this, the correct answer here actually is A. Whoever answered A is actually right. A is the correct answer. Very, very good, everybody. I'm moving on to the next question. This question I'm going to give you as homework because this is once again once again a ring expansion question. I just explained it to you how ring expansion happens, right? So what you have to do, you just have to try and form a ring. What you will get? You will get two 6-membered ring in this case. How you will get it? How will you approach it? In the notes, I will provide the answer, but first, right, on the Telegram channel, I will definitely provide the answer, but first try to do this by your hand in your notebook. That's why I've attached it. This is once again a homework question for you guys. Okay? Try to form a 6-membered ring out of it. Now, this is how 6-membered ring will be formed, but afterwards you have to look into it. First of all, try to do this on your own. Okay? Now, this question, answer this question for me. Compound A formed in the following reaction reacts with B, gives the product C, find out A and B. Again, very important. I will teach you the basics of chemistry, how to approach these kind of questions, what to look for in that. So, the reaction given to you is CH3, right? CH3, C triple bond CH plus Na. Isn't it? Isn't it? Now, what do you know about this hydrogen attached to the sp carbon? What is about this hydrogen? This is a very acidic hydrogen. Yes, right now we did it. That it is very easy to give this hydrogen away because this is once again a sp hybridized carbon, isn't it? So, the negative charge is very much stable on it. So, what will happen in presence of sodium? We all know sodium is a metal. Hence, it will always try to gain a positive charge on itself. All the metals want a positive charge on themselves because they are very electropositive in nature. So, the first reaction would be CH3, C triple bond C, Na plus and C minus. Isn't it? So, this is very, very easy to form because this hydrogen bacha is very, very acidic. The acetylene hydrogen is very, very acidic. This is your product number A. Now, with B, you are getting this kind of addition product plus NaBr as a side product, which means some bromine compound was added there, right? So, to this minus, I need some bromine compound. It can be a very normal propene. So, if I add a normal CH3, CH2, CH2Br to it, what is the property of this compound? Can you see Br, bromine, is a halogen. Hence, it is a very, very electronegative compound. This will have a delta negative charge on it. Therefore, this carbon will have a delta positive charge on it. Simple. Now, what can happen? This electronegative carbon can attack this positive carbon and hence, this is the B molecule which will give you the addition product like CH3, C triple bond C. Here it will be CH2, CH2 and CH3, right? And NaBr as a side product. Everybody understood? This is how you get this reaction. This is the same thing written over there. So you understood the basic thing. First of all, I identified the acidic hydrogen, easy to take away. And then it will become a C minus and Na plus. Then what can I do to get this kind of product and a byproduct, that is NaBr? What can I do? Then I can attach some normal propyl bromide to it. So you just have to apply basics of chemistry. You can even look at the options, right? And just try the hit and trial method, right? Very easy. Know the basics, which will get a delta positive, which will get a delta negative, which hydrogen is easy to go away, which can get a negative charge, which negative positive can attract with each other. That's what we're going to learn in this session. Very important. Understand these things. Very basics of chemistry. Okay? Chalo. Next question. These are very important reagents asked every year once again. First of all, you've been given a ethyl bromide, reacting it with alcoholic KOH. Okay? So, first molecule you have is a CH3, CH2Br molecule. When you are reacting it with alcoholic KOH, what happens? Alcoholic KOH is responsible to make alkenes. Understand this, right? Alkenes, which means minus HBr will happen and a normal CH2 double bond CH2 alkene will be formed, isn't it? Now next you are adding Br2 in CCl4. Br2 in CCl4. We just did this reaction. What happens? To both the double bonds, bromine gets attached, isn't it? So what will happen? CH2Br, and here also CH2Br will happen. Okay? Now you are adding KCN in axis. KCN in axis, which means what? The next step will be CH2, CH2. Here the CN will come. Here the CN will come. Because CN will replace this bromine over here, because bromine is a very, very good leaving group, right? It will leave and it is replaced by CN now. The next is H3O plus, H3O plus, which means what? It is hydrolyzing this thing. What can it hydrolyze? It can hydrolyze the nitrile over here. Understand this. So what will happen? You will get a CH2, CH2. Here will be the COOH species. Here will be once again the COOH species, right? So you are getting this product once again. So what is the name of this product? This is actually succinic acid. So you have to be very careful with even the common names given in your NCERT. Succinic acid is given in your NCERT. Okay? C. Correct answer is C, bacha, not B. This is not oxalic acid. This is succinic acid. Okay? The correct answer is C. Okay? Chalo. You must know what are the properties of these, all of these reagents, because these are repetitive. Every year they will be asked. Alcoholic KOH, favorite of the examiner. Br2CCl4, favorite. H nu in Cl2, favorite of examiner. So very important reagents. Now look at this. So recently these kind of reagents have been repeating in your exam. So that's why I've included this. Recently they are focusing on more name reactions, basic chemistry in your NCERT chemistry, right? So this reaction is once again, very, very important. Answer this question for me. In the given reaction, identify the reagent A and reagent B. This is that kind of question. Either you know the answer to this or you don't know. There is no in between. You cannot guess. You cannot guess what can be A and what can be B, right? Like in other that in the reaction that we just did, most of the time you could guess, right? Ki, haan ma'am, the hydrogen is acidic, it will go away. The sodium was positive, so it will take the turn. So now what will happen? The negative will attack the positive. Simple reaction. Here it is not that way. Here you have to know the specific reagent. Otherwise you will not get the answer. For example, the B reagent over here is actually a very, very famous Ethane oxidation. Ethane oxidation reagent is also again a name reaction, right? So try to answer this question for me. Answer I am getting is B. Most of the people are answering B. Nikhil, ordinary person, SV, Chandrakala, hi Puchuk Puchuk, Chalo, Sanjay, B. Very good. B is the correct answer. B is the correct answer. This is how the reaction actually goes, bacha. So in presence of CrO3, actually what happens? What is happening? CrO3 is a oxidizing agent. You're trying to oxidize this, right? From CH3, from toluene, we are making at the end you are making a aldehyde. So you are oxidizing it. So whenever, bacha, I'll tell you one more thing. Whenever, bacha, what you are doing, this is your CH3 or whatever. This is your toluene over here. Okay? So whenever you're trying to oxidize a benzene ring, whenever there is an alkyl group present over here trying to oxidize it, then directly, bacha, it gets converted into benzoic acid. Okay? No matter what is attached over here, no matter what kind of alkyl chain is attached, it will always get converted into benzoic acid except if any tertiary alkyl group is attached. So tertiary alkyl groups do not undergo any kind of oxidation. Remember this thing. Okay? All other alkyl groups will directly convert into benzoic acid. Okay? But what you have to do, you have to get an aldehyde group from this toluene as the end product, as you can see. Okay? So what we are doing, we are actually limiting the oxidation. We are using a milder reagent. So to use the milder reagents, we have two options. One is CrO3 in presence of CH3CO2 whole twice, and then you get this kind of intermediate product, and then at the end you get the aldehyde product. Or you can do Ethane oxidation in the presence of CrO2, Cl2 and CS2. This is called Ethane oxidation. Once again you get the intermediate product, and when you hydrolyze it, at the end you're getting a benzaldehyde. Okay? So what you are doing, you are limiting the oxidation using these reagents. So therefore these are important reagents. ठीक है? चलो. Next, the final product A formed in the following multi-step reaction sequences. What do you think should be the final product? This is the reaction given to you. Very, very crucial reaction. Now, see, all of these reagents have already used it. First reagent is H2OH+. What will happen with that? Try to answer this. Try to use your brain. What will happen? We have an alkene. So, okay, ma'am. The first step seems to be we have an alkene with us and a H2OH+. Hence, OH will get attached over here and this will, a product like this will be formed, right? Now, the next step is oxidation. Can you see? CrO3. CrO3 is what? Oxidizing agent. Hence, the alcohol can be oxidized over here, isn't it? So, the alcohol over here can be oxidized because this is a secondary alcohol. So, this will get oxidized into ketone, isn't it? Then we have a NH2NH2KOH reagent. What is this reagent? Very famous Wolff-Kishner reagent, isn't it? Wolff-Kishner reduction will happen. So, the final product that you're going to get it after Wolff-Kishner reduction, what happens? This gets reduced to a normal alkane. So, this is the final product that you're going to get. So, the correct answer is A. Understood this? Very, very basic reactions are asked. Very basic. First of all, H2OH plus what will happen? Then CrO3, I can see it is a oxidizing agent. So, the OH will be oxidized. Secondary alcohols gets oxidized into ketone. Then is a Wolff-Kishner reagent given. Wolff-Kishner reagent does what? Converts the ketone to directly normal alkane. So, this is the final product that you're getting. ठीक है? चलो. A, very good, very good. The correct answer is A, very, very good. Chalo, next question. Next question. This is we've already done. Try to answer this question for me. The final product A formed in the following reaction sequence. So you have another alkene given to you. First is BH3. It is hydroboration oxidation done. First, second is hydroboration oxidation. Then is the addition of HBr. Then is your Mg ether, which is your Grignard reagent. You're forming Grignard reagent and then reacting it with HCHO, H3O plus. What should be the product? Try to answer this. Try to make this. Try to do this question. Okay. I will also solve it. You also solve it side by side. So the reactant is PHCH double bond CH2 given, isn't it? First is hydroboration oxidation. What happens in that case? Anti-Markovnikov addition, right? Anti-Markovnikov means what? This is PH, this is CH. Here another hydrogen would be added and here it would be CH2OH, right? So anti-Markovnikov addition of OH has been done. Now next is the addition of HBr. HBr. What is the purpose of HBr here? HBr will do what? Will replace this OH from here with bromine, isn't it? So the product will be PHCH2, CH2Br. Same product, Br replaced, oxygen was replaced by Br. Now you're doing the Grignard reagent thing. You're forming the Grignard reagent with magnesium. What will happen? PHCH2, CH2Mg Br, right? Magnesium will get a positive charge on it. So this CH2 instead will get a delta negative on it, isn't it? Now you're trying to react it with, HC double bond OH, right? This you are trying to react it with. So what is the property of this formaldehyde? The carbon here has a delta positive charge, isn't it? So this delta negative will now get attached to this delta positive. So the final product will be PHCH2, CH2. Here will be C and then you are also hydrolyzing it. So it will be CH2OH. This will be the product. This will be the product. ठीक है? So this is the final product that you're getting. Everybody understood? Everybody understood this thing. So the correct answer is C. C is the correct answer. ठीक है, very good. So many people have already done it. Proud of you, proud of you, proud of you. SV Prasad, yes, very good, very good. Chalo, chalo. Let us go to the next question. Next question on your screen. Again, a very important reagent on your screen. The major product formed in the following reaction. So you've been given some kind of reaction. What would be the major product? What kind of reagent is this? Who can answer this? What kind of reagent is this? What does this reagent do? This is Clemmensen reduction. What is this? This is Clemmensen reduction, isn't it? This is a Clemmensen reagent. What it does? It actually reduces the CHO part, isn't it? Isn't it? It reduces the CHO to absolutely alkane. Correct answer have already gotten C, Uchak Puchak. Yes, Uchak Puchak, it is Clemmensen. Sanjay has written A is the answer to this. Let us see what should be the answer. Let us try to solve this question. So with zinc amalgam, what will happen to this reagent? First of all, this is C6H5, CHOH, right? Here is the CH3. Here is the CH2. With Clemmensen reduction, bacha, the aldehydes get reduced to simple alkanes. So it will become again a CH3 compound. Okay? At the end, this is the product. Now, next is what do you have? Another thing in your compound is a HCl. HCl can break down into H plus and Cl minus, isn't it? Isn't it? And can you see there is a OH present over here and you're also heating it. So whenever heating is there, then you have to like make an alkene there. Whenever this heat, this delta means what? You're heating it. So whenever heat is there, you definitely have to make an alkene. Definitely alkene will be a product, especially if OH is present. So what will happen? This lone pair of electrons on oxygen will attack this H over here, right? And what will happen? C6H5, CH, and this OH2 will leave. And here a double bond will be created like this. CH3, here it is CH2, CH3. So in the end, because of the heat, this OH and the H from here leaves and a double bond is created and this kind of alkene will be formed. This is the final product because HCl was there and you're also heating it. So HCl will do what? It will give the H plus and the H plus will get attached to the lone pair of electrons on the oxygen and it will leave. Right, this is a very good leaving group, it will leave and the final product you're getting is an alkene over here. Right, right, correct. Okay, so the correct answer from here seems to be, one second, OH leaves from here, right, Acha, because there's a carbocation formation, bacha, can everybody see this carbocation? Can there be a rearrangement possible as well? Right, because the carbocation is formed. But this is already a benzylic carbocation, right? This is already a benzylic carbocation. If you want, you can also do the rearrangement over here and then you can get an alkene. So the correct answer seems to be C to me. So the correct answer seems to be D to me. Correct answer seems to me, ठीक है, D. ठीक है, चलो. Next, find out the major product from the following reaction. Again, a very, very beautiful reaction. I'm going to teach you a lot of things from this. A lot of things. Because, bacha, there is a possibility of rearrangement as well. There is a possibility. If there was no, it was already stable. I agree to that. Okay, both are stable. But if there is a possibility, it can happen. It can happen. Right? Chalo. Answer this question for me. What do you think? What do you think should be the answer? This is again a very beautiful question once again. Okay, let me try it. Have you seen the options, everybody? So the question given to you is just like this. So you will get used to how to use a reagent. So you don't get afraid of these reagents in exam. So this is once again an alkene and a ketone here, ma'am, and this kind of molecule. Okay? So, bacha, understand, this is a very important kind of question. What is the very first reagent given to you? It is a Grignard reagent. Everybody can see that? Now you will ask me, ma'am, where will this Grignard reagent act? What does the Grignard reagent look like? It is CH3MgBr, right? So Mg, ma'am, here has a delta positive charge on it, and the CH3 has a delta negative charge on it. I know, right? Now this delta negative can either this, now look at this molecule entirely. What can happen? What can happen, bacha? Now, bacha, what kind of molecule you are seeing over here? Can you see that this kind of structure is being made? This kind of structure is being made. This kind of structure is actually called what? This is called alpha beta unsaturated ketone or carbonyl compound. Unsaturated carbonyls. What are they called? Alpha beta unsaturated carbon. Alpha means what? Because the carbon right next to the keto group is called the alpha carbon. This is the beta carbon. And if you count the number of carbons, and there are 1 carbon, 2 carbon, 3 carbon. Okay? So this is also alpha beta unsaturated carbonyl. Can everybody see that? Okay? Alpha beta unsaturated carbonyl. Now, bacha, in this type of reactions, always, whenever you get a alpha beta unsaturated, what you will do, you will actually perform a resonating structure out of it. What is the resonating structure? The resonating structure is this can go over here and this can either go over here, right? This can happen, or either another thing can also happen. The other thing is this can move over here and this can also move over here, right? So two kind of things can happen. So this thing is very much possible. What will happen? What will happen to the resonating structure? What will happen to the resonating structure, bacha? Here the O was there, right? The O was there. So here this gets converted into here, and this itself get a negative charge over here, and here there was already a methyl group present. Okay? Now what you have to do, you have to attach this MEMGBr group, isn't it? MEMGBr. Now where will the methyl group attack? So the methyl group now attack to a carbocation group. So if I actually move it the other way, then I can create a carbocation here as well. So if I do that and a carbocation is created here, then the MEMGBr will be added over here. This negative group will be added over here, right? Now what is the next part? Next is the addition of normal propyl iodide. So here I have already added the methyl group. Next is the normal propyl group, right? Now the propyl iodide, again iodine will get a negative charge, propene will get a positive charge on it. So now I have to look for that thing which has a negative charge on it. So now where is the negative charge coming? Once again, the negative charge, if I once again draw the resonating structures, then the negative charge comes over here. So if I once again draw the resonating structure, the negative charge comes over here. The Me was already here, the other Me was already here. So this positive, this negative will now attack this positive. So the propyl group will attach over here. So this is the final product. Okay? 2 Mes here and the other propyl group here. So always, whenever an alpha beta unsaturated compound will be there, first addition will always be at this 4th position. Remember this thing. Okay? This is one way to remember. If you don't want to remember the entire mechanism, the first addition will always be to this double bond. Okay? To the 4th atom. What is the 4th atom? This is the 1st atom, 2nd atom, 3rd atom and 4th atom. So first addition is to the 4th atom. Then the next addition is to this atom due to again resonance. Okay? Understood this part? Understood this part, everybody? Chalo. So the correct answer here becomes A once again. Chalo. Next question on the screen. Again a very beautiful question. Basic chemistry question on the screen. Basics of chemistry. Basics of chemistry. Yes, the correct answer was A. Answer this question for me. Who can answer this question for me? Try to solve this. What you are seeing, the reagent here is HF and heat. That is it. There is a benzene ring and a alkene and a HF plus heat. Very beautiful reaction. Very basics of chemistry reaction. Very basics of chemistry. Very, very basics of chemistry reaction. Somebody is saying to explain the previous question one more time. Okay, I will do that. Just let us focus on this and then I'll again go back to that. Okay. Chalo. So what is happening here? Can you see that there is an alkene present? Let me try to explain it to you. One kind of alkene is there and you're trying to react it with HF. This is again an acid, which means fluorine gets a negative charge, hydrogen gets a positive charge, right? Now this is a double bond. What is the nature of double bond? It is electron rich, hence it will attack this positive over here. When it will attack this positive over here, what will be the reaction? What will be the reaction? Here, bacha, what will happen? The hydrogen will attach on this carbon and the positive charge will come on this carbon, isn't it? Why does it happen? Why did the positive charge not come over here? Because this is making it a 1, 2, 3 tertiary carbocation, right? This is becoming a tertiary carbocation from here. So this is a more stable carbocation form. Understood this part? Now what do you have? You're reacting it with a benzene ring. Now you're reacting this positive charge with a benzene ring. And we all know benzene show which kind of reactions? Benzene show electrophilic aromatic substitution reactions, isn't it? Which means some electrophile can attach. Isn't this an electrophile? This has a positive charge on it. So this will act as a very good electrophile. Now this benzene ring will attack this positive charge. Hence the final product that you will get is a benzene ring over here, right? And then it will get attached to this positive charge cyclohexane ring, and this already has a methyl over here. So this is the final compound form. What did he do? So just look at these steps. Very basic chemistry use. First of all, HF, as you can see, it is an acid. It will get separated as H plus and F minus. Now we have a double bond. Double bond is electron rich. Hence it will attack this H plus. It will attack this H plus and then hydrogen will add on one carbon and the carbocation will form on the other carbon. Where the carbocation will be formed? Which will be more stable, right? So because tertiary carbocation is more stable, this will be formed. Now this is a positive species, hence can act as an electrophile. Hence can definitely attack a benzene ring because benzene show electrophilic aromatic substitution reactions. Hence this is the final product that will be formed. Easy, easy peasy. ठीक है? ठीक है? Hi Andhra Pradesh. Hello. Chalo. Hello to Andhra Pradesh, I mean. Chalo, understood? Now next question. This is once again a ozonolysis question. Very important set of reactions asked every year. Ozonolysis, very important reaction once again. So you have a hydrocarbon X with the formula C6H8. What do you think is the structure of C6H8? Which uses 2 moles of hydrogen on catalytic hydrogenation of its 1 mole. On ozonolysis, X yields 2 moles of methane dicarbonaldehyde. The hydrocarbon X is. The hydrocarbon X is. Who can answer this question for me? Beta, we can do as many questions as you want. Okay? If you're getting tired, I'll extend it till 8:30. Okay? And then we'll stop. And I'll give you more questions in PDF in on the Telegram channel as always. Right? Chalo, you're from Japan. Hi, Ishwari. Chalo. Yeah, that's the thing. That's the beauty of organic chemistry. You just have to eliminate some things. Uchuk Puchuk is saying I added fluorine, ma'am. No, bacha, fluorine won't be added because you have a very, very electron-rich benzene ring with you, right? Electron-rich benzene ring. Okay. Chalo, option 3. Option 3, I've already got the answer. So what can be C6H8? The product C6 means carbon 6. And I can see that this is a cyclohexene, which is C6H8. These kind of cyclohexene has to be there. Because if I do its ozonolysis, which happens what? The double bond breaks from the middle. And what is the product formed? The product formed is a double bond gets broken down into double bond O plus. This again gets broken down into double bond O and double bond O group. Isn't it? This is how the ozonolysis product we get. So X yields 2 moles of methane dicarbonaldehyde. Isn't it methane dicarbonaldehyde, right? So this is how we are getting 2 moles of methane dicarbonaldehyde. So the hydrocarbon X actually is cyclohexa 1, 2, 3, 4. Cyclohexa 1, 4 diene. So the correct answer is B. Whoever answered B is correct. Whoever answered B is correct. Cyclohexa, see, you have to again look at the naming. The naming would be 1, 2, 3, 4. This is how the naming will be done. So 1, 2, 3, 4, 1, 4 diene would be the correct name. All other names are wrong. This is how the naming is done. ठीक है? ठीक है? चलो. Not C. The correct answer is B. The correct answer is B. Chalo. I'm moving on to the next question. Again, this is a very beautiful question on your screen. Once again, choose the correct state of reagents for the conversion. You have a this product. You have a CH double bond CH3. You have a pH here, CH3 here. You have a H here and a H here. So you have a trans product and you want to convert the same into a cis product like this. CH3. Here is the pH, here is the H, and here is the H. So, what reagents should you use to convert this trans alkene to a cis alkene? That is the question asked. What reagents can you use? Just see here already the work is very much easier because the reagents are not that east and west to each other, north and south to each other. They're quite similar reagents given. You just have to guess what can be the process. What can be the process? हाँ मैं पानी पीऊंगी after the class is over बच्चा. अंशिला बोल रही है मैम केमिस्ट्री समझ नहीं आती बेटा. If you don't, the only method to understand chemistry is to do it. To take a copy and a pen and just start drawing the molecules. Otherwise, you'll never get it. If you look at these things that I'm solving and just look at them and not perform anything on the paper, you'll retain nothing in your brain. Doing chemistry is very important, right? Otherwise, it's very easy. It's the easiest subject, especially for JEE students. There's no better easy subject than them. Beta, I'll drink some water. I don't have it here. I have to just go to the other room to get it. Chalo. ठीक है. So what can you do? Let us answer this. Let us answer this. Let me remove this once again. Erase all ink on slide. Try to solve this question. So we have a trans thing over here. The trans is again, I'm drawing this. C, here is pH, here is H, here is a double bond, here is again C, here is H, here is CH3, right? So what is the first step that you can do, bacha? You can actually add an aqueous KOH on it, right? You already have an alkene, so you can convert it into Br2 and aqueous KOH. Aqueous KOH. ठीक है, Br2 and aqueous KOH should be the first thing to do, right? Or Br2 alcoholic KOH. ठीक है, now what can happen? What can happen? Here it is C. It will get converted into C. Here it is pH. Here it is H. Here it is OH. Here it is H. Here it is CH3. And here is again your Br, right? Now what can be the other step? The other step would be, so first step would be just Br2 bacha. Then we will add the aqueous KOH part. Just try to add the Br2 molecule, right? So after the Br2, it will be C. Here is the pH, here is the H, here is the Br, here is again the Br, here is again the H, and here is again the CH3. Now the next step should be alcoholic KOH to again convert it into alkene. So alcoholic KOH. So now we're going to convert it into alkene plus NaH2. What does it do? It directly converts it into a alkyne molecule. So what do I get? I get an alkyne molecule like C triple bond C. Here is the pH molecule over here and here is the CH3 molecule over here, right? The next is sodium and liquid ammonia, which is again hydrogenation, and sodium and liquid ammonia hydrogenation and the H2 Lindlar's catalyst. So H2 Lindlar's catalyst hydrogenation is actually cis hydrogenation, and we want a cis product, so we will use H2 Lindlar's catalyst, right? And what will happen? It will convert into PH, C, double bond C. Here is the CH3, here is the H, and here is the H once again. So here how you will get a cis product from trans to cis. What did I do? First of all, I added bromine. After addition of bromine, I again did alcoholic QH in presence of NaNH2, which directly converts into alkyne. After converting into alkyne, I added H2 Lindlar's catalyst to it to get a cis product because I needed a cis alkene. So I landed from a trans to a cis alkene just like this. Understood? Understood everybody? But this is an English channel. I cannot talk in Hindi. This is an English channel. We have a separate Hindi channel for Hindi audience, right? Now look at this question again, a very beautiful question where you have to react the alkene with the hot H2SO4 and a cold H2SO4. Who can answer this question for me? Hot H2SO4 and a cold H2SO4. Yes. Hot H2SO4 and a cold H2SO4. Try to solve this question with me. Whether in this, what happens with the cold H2SO4, the reaction is very simple. I'm going to teach you with the cold first. It is CH3, CH3, right? Here is the double bond and here is the CH2, right? H2SO4 means what? H2SO4 can break down as H plus and SO3H minus, isn't it? Isn't it? Now, bacha, what can happen? The first reaction could be, the first would be the addition of H plus CH3, CH3, and here the H will be added, CH2 and H, and here the carbocation will be formed, right? Now, SO minus 3H will attack this carbocation and you will get a CH3C, CH3. Here it will be the SO3H and CH3 product. So this is your product number A. With cold H2SO4, this will be your product number A. Understood? This is the product number A. So the answer is OSO3H. So it could be either A or B, right? So this is the correct answer. Now let us do with the hot H2SO4. The hot H2SO4, what will happen? Once again, I'm drawing the alkene. It is C double bond CH2, CH3. Here is the CH3 once again, right? And I'm doing the hot H2SO4. I'm trying to react it with hot H2SO4 at 80 degrees Celsius. Again, what it will do? It will once again give the H plus away. H plus it will give. So I will once again get a carbocation like this. CH3, C, CH3, carbocation, and here again CH3. Okay? Now this is a very, very active carbocation and a very, very active alkene over here. Why? Because the conditions are hot. In hot conditions, every species is very reactive. Now, can you see this alkene over here is electron rich, the double bond. So, this double bond will now attack this positive charge. So, now what will happen after this double bond attacks this positive charge? CH3, CH3. Now, this double bond will get attached here like CH here, and here it will be again CH2. Here it will be double bond C, CH3 and CH3. So this is the final product that you're going to get. A double bond will directly attack your carbocation over there, and this is the product that you're going to get with hot H2SO4. So with hot H2SO4, you're getting a addition product. Why? Because the conditions are hot and every species is hot. So after the formation of carbocation, the double bond on the same molecule itself will attack this carbocation and form an addition product just like this. With hot condition, with cold condition, there was a OSO3H product formed. Hence the correct answer, correct answer is A. Right? This and this. The correct answer is A. Understood? Correct answer is A. Very good, very, very good everybody. Very, very good. Okay? Let us move on to the next question. This is I'm again giving you as homework. Why? Because this is again that kind of question where if you know the reagent, then you can solve this. This is once again I'm telling you from the chapter hydrocarbons. Okay, and which reaction is that? I'm also telling you that in your chapter hydrocarbons, there is a reaction called aromatization. Aromatization. What do? You make an aromatic compound out of a simple alkane. Using which reagent? Now you have to answer to me. Using which reagent do I form an aromatic compound? Right? Okay, this is in your hydrocarbon chapter. This is the second homework question. What questions I'm giving to you so that you open your brain. Understand, these questions are actually asked in your exam. Correct? Correct. Let us move forward. Already people are giving me the answer A. You are absolutely correct. Absolutely correct. Okay. Chalo, next is major product of this reaction. Again, a very beautiful question. Beautiful question. Try to answer this. See, you have this kind of complex molecule given to you and you have to react it with two HBr molecules, right? I'm again going to draw this molecule. It is 1, 2, 3 oxygen, la la la, this double bond O, and I'm trying to react it with 2 moles of HBr. Okay, HBr. What is the property of HBr? It will break down as H plus and Br minus ion, isn't it? Now, bacha, you have 2 alkenes to attack the H plus ion, right? So, which will be the first alkene to attack? This can be the first alkene to attack because this is so much into resonance, right? So, what will happen? What will happen? This alkene can attack this H plus over here. Then, what will be the next step? The next step will be this double bond O, right? Now, where here the positive charge can come, and here the hydrogen can attach itself, right? Here once again the oxygen is there, here SA, here. The positive charge comes over here. Okay? Now, is this positive charge stable? Is the positive charge stable over here? Is the positive charge stable over here? Answer this question for me. Can you see here electron withdrawing groups are attached, right? Electron withdrawing groups are attached, hence this positive charge is not stable. That should be your counter question to me, ma'am. Here already a electron withdrawing group is attached, like C double bond O is withdrawing electron and he already has a positive charge. So this is very, very unstable. So what actually ends up happening, even though this is a secondary carbocation, okay? Even though this is a secondary carbocation over here, okay? So, this is a not stable carbocation. So, here the Br minus, can attack and can form a Br over here, right? Right? Or, okay, this is again a positive charge over here. Here it can form or here it can form. This is actually taking away the electrons from here because this is electron negative over here. This is causing the minus I effect, against destabilizing negative charge. Correct, correct. So the Br, one of the Br will come here. Now let us look at the next kind of here. See, there are so many options available. There are so many options available where the Br will attach. So one Br can attach over here because the secondary carbocation. Next case where the Br will attach, once again. Here can you see the Br, the positive charge is actually not stable over here because negative I group is over here. The oxygen is showing minus I effect. Minus I, it is extracting more electrons from here. So actually once again the positive charge is actually stable over here and the Br gets attached over here and the H gets attached over here. So the correct answer seems to be the A option. Correct? Correct? Chalo. Now this is once again a very important question from your oxidation point of view. So I will keep the session till here. Okay? Till now we have tried to solve so many questions, try to see the stability of so many carbocations and carboanions over here. Okay? And this is once again an oxidation basis of question. This is again, I'm giving you the last third homework question. Try to do it. It's not very difficult. This is once again a homework question over here. Beta, this last question that I just explained, right? So what do I think? According to me, I'm also viewing this question. According to me, I think the answer A is correct, right? But I will let you know the correct answer in your PDF box, because here I am having one doubt. The doubt is, if I create a positive charge over here, right? So if I create a positive charge over here, this is actually an electron withdrawing group. So this positive charge is not stable here, right? So once again, if I am creating a positive charge over here, once again, the oxygen here is actually a minus I group, right? So oxygen here is pulling electrons. So again, the positive charge is not stable over here. So there is actually a little bit of doubt whether the positive charge is stable over here or here or here, right? So this is a very beautiful question. But right now, let me check what your NTA has given the answer, right? I will let you know in the Telegram channel for sure the correct answer would be there. But right now, I'm having an issue in this question. ठीक है? चलो. Yes, either C or D. No, but it not can be either C or D. It can be either A or C. है ना? Let us see what actually happens. Now, this is a homework question for you. Again. Acha, for this you are saying either it can be C or D. Yes, it can either be C or D. That is correct. That is correct. Chalo. And I will see you again. Yes, a positive is unstable. That is correct. But also you have to take into account that their secondary carbocation is forming. So is the stability of secondary carbocation more? But also the electron withdrawing group is there. So there is a, but that secondary carbocation over here. No. That is correct. That is correct. The carbocation over here can actually go into resonance, right? So this is a stable carbocation. My answer is correct. But here it cannot go into resonance. So this Br will be stable over here. Yeah. So this is the correct answer, bacha. This A is definitely the correct answer. So what we have to see? You have to see the stability of the positive group. So this positive over here can actually participate in resonance, right? This can go over here, this can go over here, right? So the positive charge is participating in resonance, so this Br will definitely come over here, right? So this is the only option with this Br. But here, if the positive charge comes over here, a minus I group is over here, right? So this minus I is decreasing the stability of positive charge. So the positive will be stable over here. So A seems to be the correct option. This positive is not stable, right? So the Br will actually attack on this positive, not this positive. So this is the correct answer. That one is the correct answer. Got it? Thank you. It's the correct. It's the correct. ठीक है? चलो. This is again homework question. Very easy. And I will see you once again tomorrow, and then again day after tomorrow. We're going to do so many of organic chemistry questions. If you have any doubts, especially from this session, I'm going to send you the PDF in those questions. If you have any doubt, please ask me right and then in the live classes, so that we interact with each other like how it's supposed to. And also a new series is coming for you guys. Please get excited for it. All the nitty bits of organic chemistry in like 15 minutes video I've compiled and concised videos are already prepared for you guys. Tomorrow will be the launch day for the series. Stay tuned for the perfect organic chemistry series, the ultimate solution to all your organic questions. Like 5, 10 to 15 minutes videos are there on each and every topic. You can make use of them. Tomorrow I will officially officiate that series. Thank you guys so much for attending the class. Thank you so much. Bye.